me that I've got to sort out a way that BGS is going to quantify uncertainty in the data sets and information it makes available to decision makers and modelers. So my plan for this talk is basically to give you the context of what decision-making work we do at BGS, how we're involved, to let you know what progress we've made in quantifying uncertainty in the various products, and then hopefully by lunchtime you can tell me how to finish it off and I can tick off my forward job plan. So to give you the context, BGS was founded in 1835. As the name suggests, we're meant to be making we're meant to have made a geological survey of Britain and Northern Ireland, and we dragged it out for as long as we can, but now we have at least got a version that is finished, and this is the map of the UK bedrock. It is available, as somebody reminded me yesterday, it is available as an app, it's available as a jigsaw, very reasonably priced from the BGS shop. But we also hope that it is quite useful as an input to some landscape scale models. So if you want to know about whether land is suitable for building certain infrastructure, if you want to know where water's going to go, whether it's going to be stored underground, there's useful information in this. So, having done a 2D map of the United Kingdom and still needing to justify our existence, the obvious next step is to move into 3D. 4D has started, but I won't be talking about that. And we now have a national geological model which is in 3D, and this is much closer to the sort of impacts which will go into the hydrojewels project that Simon was talking about on Wednesday whenever we started. And this starts to give you information about the sort of volumes of water that can be stored underground, the directions that they might be moved in, and obviously in other applications for underground infrastructure, gives you the information for what's possible and what isn't. This next slide comes from our marketing department, so I'm not 100% sure what it means, but the message I'm trying to get across is that we now do a lot more than geological surveys. We're basically anything underground and a few things above ground we do work on. So trying to think of examples from the top of my head that include carbon storage, groundwater quality, groundwater levels, floods and droughts, space weather somehow gets into our remits, coastal vulnerability, energy from geothermal, soils, basically any earth science application we make a claim on. These activities also create a lot of data. So in the soils context, we're particularly keen on urban soils, and we sample those at quite a large, I think it's something like 4 samples per kilometre. So we've got very nice urban soil data sets. We've also sampled, for the majority of England at least, rural soils at a fairly high density. But the people who use this information, they don't tend to want the raw data. It's only soil scientists who ask us for that. And I say, if you do want the raw data, I think you can ask DEFRA for it, and they give it out. But most of the people who want our soils information actually want a nice gridded product to know for every kilometre what we think in this case, carbon concentration is. So that's one way we're providing information to modelers. As we get closer to decision makers, we tend to be doing more processing of the data. So again, for my own selfish context, I'm currently buying a house. My solicitor has paid BGS. I could have got this information off one of our hard drives quite easily, but I thought that's probably not allowed. For reports on the location of my house. So questions like, is it a radon affected area, potential for subsidence, potential for groundwater flooding. These aren't the pictures from my house, by the way. Mine was a lot better than this. But these are based on our basic geological models. A bit of expert knowledge, a bit of processing comes out as these statements where we give advice to the decision maker, in this case me, but with a few caveats about we can't be totally sure. But obviously, important as my house purchase is, it's not really a landscape scale decision. But we do this sort of work at the landscape scale. So thinking about as civil engineers, we have a range of civils products that will tell somebody thinking about building infrastructure anywhere information that they'll find useful in terms of whether the ground can cope with the structure, whether they can dispose of the excavated material safely without dangerous things leaching into groundwater. So that's an example of the sort of products we'd be giving out to decision makers at a larger scale. Another example is thinking about coastal erosion, that again, we would join up a few of our data sets, so susceptibility to erosion, flood susceptibility, cliff top height even, to build a product of the potential for coastal erosion and inform decisions about where needs protecting and where it's safe to build. And we've also dabbled in the area of decision support tools. So this is one. This was actually done by my brother, so please criticise it all you like. But this is looking at different renewable energy sources and the suitability for whatever location you want to say in the UK. So it's a nice little app. There's lots of data behind it, not just ours, other people's. I think these pictures are looking at ground source heat pumps. So in terms of the resource, the underground temperature profile is obviously the most important thing. There's various constraints on where you can put these things, either because the land is too valuable for another purpose, or because you just can't put the infrastructure in. And this will come out of a decision on what your land is suitable for you, and we'll even email it to you at the end. And the final example I was going to put up is something a more bespoke study. So it would have started off with the basic BGS model, but then look in much more detail. And this is the building of the Crossrail stations in London. This one particularly, Farringdon. So we would have had our geological model for London, but we'd have looked in much more detail where they were planning on digging the tunnels for Farringdon, and being able to inform about where they're likely to run into faults and potential difficulties, where they're going to run into what do we call these, sand deposits, which basically might be holding water, and again would cause trouble for the people doing the building. So, and I think that these end bits are just comparing with our existing model. So that's given you sort of something on the range of ways that we're involved in decisions. We're helping out decision makers. It doesn't tend to be that we're building the big landscape models that other people have shown here, but we are providing information that might be going into these models, and we're also doing some interpretations of our own that go directly to decision makers who will use the information we give them. I should say I have a tendency to call the things that we make products. A lot of them are freely available. If you Google BGS Open Geoscience, there'll be a big list of products and things that are freely available. Some of them are kind of low resolution, so the things that we sell. Others are raw data. You can also go to the what do we call this? The map view, BGS map viewing page. The address is at the top, and this gives various pretty products or maps of our different data sets, and also given the company in the room, the UK Soil Observatory also includes various CEH and Cranfield and probably Rothamsted's data sets as well. But that's a nice source of information. Some of it's freely available, some of it is licensed, and it will point you in the right direction where you get the data. But generally for academics, it's quite easy to get hold of it. So yeah, I kind of already given this summary, but BGS are providers of raw data, providers of derived products or maps, dabble in decision support tools, and we do some sort of bespoke modelling to answer specific questions for a decision maker about a specific site. But where we're going next is that we're not particularly good at putting uncertainty into these things. That if we're doing a whole process, we can model the uncertainty. But if we're providing data that anybody might use in the future, it's very hard to put uncertainty on that in a useful way. And we're trying to think of ways that just our online products that anyone can take, we can put some useful measures of uncertainty onto them. So I'll start off with an easy case. Well, this is easy for me because in the days when I was allowed to work at my computer all day, this is what this was my bread and butter, the geostatistics, to make a nice map of a soil property. So if we wanted to build what we'd call a spatial product, a map of loss and emissions, so that's carbon concentration in the southwest of England, we'd probably take the raw soils data. We'd suspect that carbon might vary with topography, so we'd throw in some topographical variables. Here it's elevation and slope. The reason we quite like focusing on the southwest is that we happen to have NERC has flown a radiometric survey of the southwest, which gives us all sorts of information about the underlying geology and hence the soil variation. So it's a very helpful covariate for using for mapping soil properties. And we're kind of plugging it because we're trying to persuade them to fund it, to fly it for the entire UK. But given all that information, we do a bit of statistical modelling, and we get a nice, relatively smooth map of how carbon varies in the southwest. And because it's a statistical model, we also get some form of map of the uncertainty. Now, soil scientists have become no longer satisfied with linear mixed models, which is the basis of this. They like trendier methods, and so do senior people in a geological survey. So we can also do the same process using quantile random forests. But it's basically, we can build a product, we can quote uncertainty. So here, the plot is just of the width of the confidence interval, which is possibly meant to be a prediction interval. But we could have quoted it in different ways. So in theory, I can tick a box and say that if, instead of just providing the nice map, we also provide a map of standard errors or something similar, I can tick the box and say we provided uncertainty information. But the thing that concerns us is whether that information is actually going to be any use to anyone, whether the modeler is actually going to use that information in their modeling process. And to some extent, it's probably going to be impossible for them to do that, because they don't have all the information that we have, that they won't know whether those errors, they're likely to treat those errors as if, or the uncertainty, as if the errors are going to be independent of each other, when in reality, they're going to be spatially correlated. They're also, these maps are produced at one scale, and the uncertainty corresponds to one scale. But it's quite probable that the end user will want to use them at a different scale, where the uncertainty will be different. And if I was the end user, I would know how to change the scale. They won't be in a position to do that. And the final question is, well, there's also a very slight issue in this case on propagation of uncertainty, that I've relied on a previous product, this TELUS Southwest radiometric survey of the Southwest, and assume that it's perfect, there's no uncertainty. But I know it's actually flown by an airplane in a load of lines that are a few hundred meters apart. So some interpolation has gone on to get the 50-meter resolution product I'm using. Now, to be honest, that propagation of uncertainty, it probably won't amount to much in my final map. But there's other BGS products where propagation of uncertainty is obviously going to be much more important. And if we go back to the home bias reports, the things that you get on your house, if you see where they're derived from, so this is the geological map for the same area, and obviously spatially the same features fall out exactly. So if we've got the boundary of a feature wrong by 50 meters, that can be the difference between it being on your land and not being on your land. So in that sort of example, the propagation of uncertainty is something we care about a lot more. But that's the relatively simple case of how we're thinking about uncertainty. When we come on to 3D geological modeling, it gets quite a bit trickier because it's a lot more complicated process. Underground, there is a load of discontinuities and faults which aren't really consistent with a nice statistical model. And there's lots of layers of different geology, which again aren't easy to account for in a single statistical model. There's also various laws of physics of deformation of rocks which have to be obeyed. And it turns all of this into a very much multi-stage process which involves a lot of interpretation rather than direct statistical or process modeling. And the other challenge I should have mentioned is that the only real sort of ground truth data, which are boreholes that we dig and record the rock as we go down, they tend to be really sparse unless it's a particularly important area. Just to emphasize the degree of interpretation that's required on these things, this one source of data we do have seismic images. So basically, we do create some vibration at the surface, see how that vibration bounces back to the surface. And as the rock type changes, you tend to get dark lines in the seismic image on the left-hand side. But I don't know how to interpret these things. You get all the sorts of problems of double images that you would see if you were reflecting light. But some geologist has come along and done this beautiful diagram of what's going on in the picture on the left, just combining their expert knowledge. But another geologist would come along and come up with a very, very different picture. And this is one of the challenges we've got, that we don't really know how to quantify that sort of uncertainty. We've had a PhD student who's given it a go, and there's two different ways he's tried. So the simple schematic at the top is, so the first way is basically he's tried to remove a borehole of the relatively few boreholes he's got, is remove one borehole, get a lot of geological modelers together, ask them to say what's going on in that borehole, where do we expect the line between these two rock types to be. And from what they've said, we've tried to work out, we've tried to model both the bias in the predictions we get from these various experts and also the range of the errors. And we tried to explain these things in terms of different factors, like the experience of the geologist, the experience of using the software, and various factors about the actual landscape that we're dealing with, its complexity, how far you are from the borehole. So he did this and has published some work in Geosphere on two different sites. So one of these is Manchester, the other is Glasgow. And he was able to build these linear models which were able to explain uncertainties, errors as it were, from the experts in terms of these various factors that I mentioned. The problem was that in the two different contexts, the key variables were different in each one. So it's not going to be a universal law that we can apply everywhere, but it's one way we can think about. The other way we considered, which got mentioned briefly yesterday, was expert elicitation. So I can't remember what the name of the elicitation that was mentioned yesterday was, but we've been using the Sheffield version, which is called Shelf. And basically what we're doing here is getting a number of geologists in the room, asking a very specific question. So we've got a borehole in the middle of this picture. We want to know where the depth of the different layers of geology that are going to occur at that site. I'm just on the last bit. So the Shelf methodology is similar to the elicitation that was described yesterday. The process has one less iteration. So basically, you get your experts together, you ask all of them what their best guess is of whatever question you're asking. Then you bring them all together to discuss what their estimates, and I should say estimates of the entire distribution. And at that stage, you try and make them form a consensus of what the group believes. So the guy who came up with Shelf refers to a rational independent observer. He asked people to sort of step back from the discussion and say, if you'd witnessed that discussion, what would your belief be about what you'd expect to see at that borehole where we don't have any measurements? And again, Charlie Randall did part this for his PhD. it produced different results to the linear models that we did last time. And to be honest, we kind of trusted the results less, that it felt like too much group dynamics was going on, influencing what we were getting as the uncertainty, rather than hard science. I thought that was the last thing. I've just realised the final point I was going to make is that we also have trouble communicating uncertain information. We've done some collaborations with psychologists and found disturbing things. So the context of this could be like if we're trying to persuade people to evacuate an area because of a threat of a volcano or landslide or something. And there's some quite disturbing results that people respond differently to if you phrase something as unlikely and tell them it's a 33% chance than if you tell them it's a 33% chance and unlikely, which I don't understand, but it worries me. We also find when we're dealing directly with decision holders that we build beautiful PDFs of what we think is going to happen. So the likelihood that we think there's going to be a drought this summer, but they don't want that. They often just want some traffic lights. Or in the case of some work I've been doing at the moment about mapping sediment classes on the seabed, they've asked for uncertainty because, like us, they know they should have uncertainty in the maps they produce. But when I've asked how that's going to be interpreted and used, they've not been able to give an answer, which means it's hard for us to decide how exactly we communicate that. So that's all I wanted to say. So hopefully the conclusions are self-apparent, and I'll stop. Thank you.